Okay, welcome back everybody. Happy Wednesday. Today is November 9. We are covering zeros of polynomial functions. You are still working on project 3, I hope, because it is due our very next class. Now, this week is a little bit different here at GCC. Friday is Veterans Day. We do not have any classes on Friday. Today is a Friday schedule, technically, even though we're a Wednesday, although I'm hoping you figured that out already because this is probably your last class of the day. So in any event, our next class is Monday coming up, and that is when the project is due, okay? Any questions on the calendar? Okay, so we're going to start not on page 24, but with a problem that sort of came up in the homework, and I didn't realize synthetic division was in the homework, and we did not talk about synthetic division at all, so we're going to do this real quick. This problem right here I grabbed from page 29 of your packet. You can go there now. I don't know if you'll have room to do what we're about to do. What we're about to do doesn't take a whole lot of room, but if you're on page 29, you'll at least be able to compare the answer that you got doing it the long division way with what we're about to do the synthetic division way. Okay, here we go. We are dividing x cubed minus 2x squared minus 5x plus 6 by x minus 3. So the very first step with synthetic division is to take this x minus 3 and change the sign. What value of x makes this thing equal to 0? 3. Like we know that 3 is an important number for that x minus 3. And so we're changing the sign with this little brackety thing over here on the left. That's the first step, is to change the sign of that number. Next, we're going to write down this thing that we're dividing into, except we're not going to write the x's. We're just going to write the coefficients. So what's the coefficient of x cubed? Is 1. And the coefficient of x squared is negative 2. And I'm imagining they just have a little space in between. So they're not connected in any way. They're just kind of floating. The next one, negative 5 and positive 6 is there. Okay, give yourself a little bit of room there. You don't want the numbers banging into each other. Okay, so let's start the synthetic division process. The very first step is to take this number and copy it straight down. Okay, and now we're going to do the process that we're going to repeat over and over again, which is just like long division, where you do like a first thing into first thing, and then put the answer, and then multiply and subtract, and then you repeat all of that, right? So that's what we're going to do here. We are going to multiply these two guys and put the answer right there. Multiply. So what do we get? 3. Excellent. One more color here. 3. In the regular long division process, it's a subtract. But here, it's an add. We'll talk about that in a bit. But we are adding to get the numbers down in the bottom row. So add, what do we get? Negative 2 and 3 is positive 1. And then we repeat. So here's the two-step process. Multiply and then add. Multiply and then add. And so we multiply. That same 3 is going to multiply by everybody. So that 3 times this one is 3. And then add. Negative 2. That 3 times that negative 2 is negative 6. And then add 0. Doesn't always happen that it's a 0. Just happens in this case. That's synthetic division. We still have to interpret the answer, but that's the process. Okay, so here's the answer. Here's how we interpret it. This very last number is always the remainder. So put a little line there. That's separate from the rest of them. The rest of them, we now finally have to put the x's back on. We ignored the x's up until now. Now, the very first one in the beginning was a 1x cubed, right? But that's not what it is here. For me, I always like to start at the right. That negative 2 is the constant. The next guy is the one that has an x on it. The next one has an x squared on it. If there were another one, it would be x cubed. And if I just put, like some addition signs in between here, then I've got my answer. The answer, looking at all of this, is x squared plus x minus 2 with a remainder of 0. How does that compare to the answer when you did it the long division way on page 29? Right, you did this one. What's the answer? It's the same, right? X squared plus x minus 2 with a remainder of 0. So when I first learned about synthetic division, it was just like witchcraft. I was just like, okay, it works, but what is going on here, right? Like, where are all the x's? And what is this magical process, multiply and add? You know, like what happened to long division? In fact, this is like as far from the long division process as you could imagine, because when you do long division, Matt told us the other day, you divide, right? First into first. It's a division. And then once we've done that division, we subtract, right? Well, what do we do here? Multiply and then add. It's like the exact opposite of what we do. But it works. We're not going to talk about the whole thing. If you want to explore why, you know, like where do these numbers appear? You did the long division problem already, the long way. You'll see all of these numbers. You just got to find them. But the only thing I'll say here is that what was the very first thing we did to get this original number? We changed the sign. That changing the sign made it so that instead of subtracting, we want to add. So like we took care of all the subtracting by just changing the sign. Okay. There should probably still be a lot of mystery associated with synthetic division, but in any event, that's part of it. Okay, so I'm sorry I didn't know homework was going to include this last time. So if you didn't get a chance to work on it now. And yeah, a 10% penalty is not that much, so don't sweat it if it's a little bit late. Questions on synthetic? Okay, so let's take a look on page 24 here. And normally we don't do the preview exercises together, but I just wanted to make some observations here about the answers. So I think the way to solve parts A and B is the quadratic formula for both. You might have gotten this guy initially, -4 plus or minus root 20 over 2. And somebody check me because I just sort of did this on the fly. Is that right? Yeah. And you can clean it up. If you clean it up, eventually you get around, I think you get to this guy, -2 plus or minus root 5. And so I'm just going to point out that the two answers here are quite similar to each other. One of them is -2 plus root 5. What's the other? What's the other answer? -2 minus root 5. Yeah, they're almost identical. Just one has a plus between and one has a minus in between. And for part B, again, a quadratic formula. Can somebody check? Is that a square root of -8 in there? Okay, and so then I cleaned that guy up and I got -2 plus or minus I root 2. And again, we get two answers. And again, they're quite similar. -2 plus I root 2 and -2 minus I root 2. And so one of the results that we're going to see in a few minutes today is that if you have, remember we talked about imaginary numbers earlier this semester. If you have an imaginary number, something that is not a real number, like -2 plus I root 2, if that's the solution to some polynomial equation, then its partner must also be a solution to that same equation. They come in pairs exactly because of that plus or minus in the quadratic formula, right? And so as soon as you have one thing with an I in it, you have the partner. Anybody remember the math word for what we call these two guys? Starts with a C. You have one and you want to get the other. It'll be from another math class. We haven't used this word, I don't think. These are called conjugates of each other. You take the first guy, the conjugate is the second guy. Or you take the second guy and the conjugate is the first guy. And the same thing is true with real answers that are irrational. So if you have a square root of 5 in your answer, for sure the partner, negative square root of 5, is going to be another answer. So they always come in pairs, these irrational numbers and these imaginary numbers. So that's coming. Okay, so we're not going to talk about two together, but let's move on to number 1 in the demo. When finding zeros of a polynomial functions, what kinds of numbers can we get? So here's a polynomial in completely factored form, and we're going to observe that all the factors are linear. So this guy is f of x equals 1 times x plus 3, 2x minus 1, x plus root 2, x minus root 2, x minus 4 plus 5i, x minus 4 minus 5i. Woohoo! Okay, one observation here. As soon as you saw this, did you recognize that there was another guy in there for sure that we were going to see? That this guy, as soon as you have root 2 as one of the answers, negative root 2 is also going to be an answer. It's automatic. It's what we saw with the plus or minus root 5 up above. And here, x minus 4 plus 5i, and then x minus 4 minus 5i. That's the same thing we just talked about, conjugates of each other. As soon as I see 4 plus 5i, automatically I know 4 minus 5i is also going to be 0, a solution. Okay, so it says find all the zeros of this polynomial, and then we'll classify stuff. So we'll just write some things down. What value of x makes this guy 0? Negative 3. How about the next one? Also negative 3. The next one, take your time there. Yeah, that's 2 steps to get there. Make sure you can do it. 2x minus 1 equals 0. It's an equation you all know how to solve, but just writing that is a step that we're not necessarily in the habit of doing. So 1/2. The next one. Negative root 2. What about the next one? Positive root 2. All right, then we get to the trickier ones here. What number for x? X minus 4 plus 5i equals 0. That's what we're solving. 4 minus 5i, not over, right? Just add and subtract them both to the right-hand side. And then this guy is x minus 4 minus 5i equals 0. And when you move them both over, what do you get? 4 plus 5i. Again, those are the conjugates we were talking about. 4 minus 5i automatically has a partner, 4 plus 5i. Okay, so lots of different kinds of numbers here. All of these guys here are real numbers. These ones here? Yeah, those are our imaginaries. I'm actually not even sure of the vocabulary myself here. I see this thing that says complex imaginary. I'm going to put a question mark. I honestly don't know the vocabulary. I think that the answer we're looking for here is complex imaginary. And it's possible that when we say imaginary number, we mean only something like 3i and not 4 plus 3i. That's my guess, is that we're calling this guy a pure imaginary. It doesn't have the real number part separately. And that this one maybe is the complex imaginary. That I don't know. Okay, so those are fine. We've also got rational and irrational numbers here. So where do the rational numbers stop in this list? Yeah, so 1/2 is rational. That's the last one that's rational. Which ones are irrational? Yeah, those 2 square root numbers are irrational. And then the ones with i's, we don't classify them as either irrational or rational. They're just a separate beast. Okay, got some more blanks down here. What is the degree of this polynomial? If you imagine multiplying all of these x's like a massive distributing thing, what will the highest power on the x be? 1, 2, 3, 4, 5, 6, 7. 7 is good. That is the degree. Right, we don't need to actually multiply it all out to know that it's going to be x to the 7th in that first term. How many linear factors does this thing have? Also 7, right? And how many zeros does it have? We wrote them in blue. 7. What we're saying is we're counting the -3, and then we're also counting the -3. So don't smush them together to make 6 zeros. Keep them separate.
So
yes. Yes. Yes, all 3 of those are going to be the same. And in fact, the degree telling you how many zeros, that's something that I shared with you guys like a month ago, right? And it's something we've been using. If you see an x cubed equation, how many answers is it going to have? It's going to have 3, right? And so we've seen this for a while now. This is sort of our official introduction to that theorem. Okay, on the next page. Let's actually skip this page temporarily and go to the page right after. I think we're ready to just look at the conclusions. We've talked about a bunch of this already. If a polynomial function is of degree n, then counting those multiple roots separately, like the -3 and the -3, the equation has exactly n zeros. Some might be real, some might be imaginary, some might be repeated, but altogether the degree and the number of solutions are exactly the same. It's not named here, but this theorem has a name, this part A. You don't need to write it, but I will tell you it is the fundamental theorem of algebra. Let's say again, the fundamental theorem of algebra. How many fundamental theorems of algebra do you think there are? One. It's that one. So when we say the fundamental theorem of algebra, we are saying this is like the backbone of algebra. That theorem right there. Part B, an nth degree polynomial, the same n we saw, can be expressed as the product of a non-zero constant, some number in the front of all those parentheses, and n linear factors, like 7 linear factors like we saw before, where each linear factor is of the form x minus c, where c is one of our zeros, right? This is just what we saw with that example. X minus some zero, x minus another zero, x minus each zero. And then part C says if a plus bi is one of the zeros, then we get another zero automatically for free. What is it? A minus bi. As soon as you have one, then the imaginary number a minus bi is also a zero. They come in partners in the quadratic formula. You know that plus or minus square root. There it is, the plus and the minus. And we talked about this word here, conjugate pairs. They're conjugates of each other. Irrational zeros also occur in conjugate pairs. So if you have 1 plus root 2, automatically you have 1 minus root 2. Okay, let's go back to the page we just skipped. Number 2. It says consider the function f of x equals x cubed plus x squared minus 5x minus 2. We're going to find the exact values of all the zeros of this polynomial and then write it in completely factored form. How many zeros are we going to get? 3. That is what we're after. Okay, finding the first zero. This is actually a problem that we did in the demo last class, but now we're going to do it again. Last class, the first zero was just given. I think it was x equals 2 or x equals -2. It just said, hey, -2 is a zero. Use it. This class, we're going to look at a picture. This is the graph of that polynomial from a graphing calculator. Do you see the 3 zeros in the picture? What do they correspond to in the picture? X-intercepts, right? We've got 3 x-intercepts. The goal is to hopefully grab one of them. I'm hoping one of them is a nice number that we can just sort of guess by looking at the picture. And you can see that, for example, this leftmost zero is someplace between -2 and -3. But I can't guess what number that is. And then the middle zero is someplace between like 0 and -1, but who knows? The last zero, I think, is the one that we want. It's actually got the sort of X marks the spot on it. Guesses for the X value? 2, just counting hash marks. And then, okay, that turns out to be a really good guess. If you look at the bottom of the screenshot, 2, 0 is where the X marks the spot is, okay? So from looking at the picture, we know X equals 2. Is a 0. Which means right away that something is a factor. X minus 2, that's it, right? We know that the zeros and the factors go hand in hand. And so what that means is that this original guy, the whole x cubed and all the other stuff, must equal x minus 2 times something. Agree? Because x minus 2 is a factor. Yeah, I mean, we're going to fill the blank in. Filling the blank in is a big part of this process. Does everybody see that's for sure what we have? Is that big blank, which we're going to figure out. And so to figure out what that big blank is, let me give you another equation. 8 equals 2 times x. How do you solve for x? Don't tell me the answer. Tell me how you solve for x. We divide by 2, right? This is the thing we are trying to find. So what should we do to that equation to solve for that thing? Is divide by x minus 2, right? Just get it onto the other side. So that's why we're doing long division, so that we can divide by x minus 2 and solve for whatever goes in the parentheses. So let's do our division. I'm going to write this. How do we want to do it? You guys want to do the division from last class, or do you want to do the synthetic division that we just saw earlier today? A couple of votes for synthetic. Yes, good, synthetic. Okay, let's do synthetic. All right, we're going to put a number out here. What is it? 2. It's not -2, +2. Change that sign. For me, the way I remember it is what makes the thing 0. 2 makes the thing 0. So we put a 2 right there. Then we're going to grab the coefficients only of this polynomial. 1, 1, -5, -2. That's what we write here. 1, 1, -5, -2. Okay, first step is easy, but it's also easy to forget because it's the only time you do it. What do? We bring that first number down. We need a way to get the ball rolling. That's how we do it. Okay, and now is the part where with a little practice you can do it pretty quick. You're multiplying and you're adding. Multiply and add. Multiply and add. Okay, so I've got these. Let's just get the last one up here. That's a 2, and then we add, and we get 0. Good. Questions about the process? Even though synthetic division is a mysterious thing, my goodness, is it efficient, right? Like that is fast. And it's compact too. You remember how much space these long division problems take up. Okay, so all we got to do is kind of get our pieces back in here. I'm going to put the line there. What is 0? Remainder. Are you surprised? You better not be surprised. In fact, if it had been anything other than 0, you should be surprised, because what we decided was that x minus 2 is a factor, meaning it went in evenly. Better not be a remainder. Okay, let's get some x's here. The 1 is the constant. This is really 3x, and this is really 1x squared, and then a couple of plus signs will fill it out. So what that means is that in the blank parentheses, we get to put what? X squared plus 3x plus 1. That's what goes up there. Okay, the goal of this problem has been to find all the zeros, which means we've been wanting to set this equal to 0, which means either the first parentheses is 0 or the second parentheses is 0. We already know what value of x makes the first parentheses 0. It is 2. So now we're on to the harder problem. What makes the second parentheses equal to 0? I don't know. I got to write it out. So we'll put that down here someplace. X squared plus 3x plus 1 equals 0. A technique to solve that equation? Quadratic formula. That's what we're doing. -3 plus or minus square root of 9 minus 4 times 1. I'll divide by 2. Anybody else confirm? -3 plus or minus root 5 all over 2. Good. Okay, so we have finished answering one of the questions. Let's just fill our answers in here. It says the 3 zeros are, there was an easy 0, nice one, 2, and then 2 irrational numbers that we just popped out. I'm going to list them separately. -3 plus root 5 over 2, along with -3 minus root 5 over 2. Those are our conjugates. And because we know the 3 zeros, we also know how to write this guy out in terms of a product of 3 factors. One of them we had up above. What was it? X minus 2, and then x minus X minus what? Yeah, it's all of that. I'm just copy it. It's X minus the entire answer from up above. And then it's X minus the other entire answer from up above. So don't get lost in the signs here. It's always X minus. Always, always, always X minus. Okay. Let's say one last thing. Do you guys remember there's typically a number in the front here? We've called it A. Right. So whatever number goes in the front there, it's a copy of the number that was in the front of the leading term. What was the number in the front of the x cubed? It's a 1. And so I'm going to put that up here. I'm going to put that 1 in green. If it's anything other than 1, you might forget to put it, and that's a problem. Whatever that number is, it's getting copied right here in the front. Because every single one of our linear factors is x minus, x minus, x minus. If you distribute all of this through just the things in black, that x is going to multiply by that x, is going to multiply by that x, and give me x cubed, and that's it. And so if the original problem up here had been 2x cubed, there's no way to get it with an x minus and an x minus and an x minus. That's the only way to make it a 2x cubed. So whatever that number is, gets copied. In fact, if I were you, I would probably copy that first. Before I did any other part of this problem, I would jump to the answer and say, oh, 2, put a 2. X minus, x minus, x minus. Okay. All right, I think we're good here. On the next page, got one last question to do. This one will be pretty quick, I think. Number 4. Says find a third-degree polynomial function. It's called f of x with real coefficients that has -3 and I as zeros, and such that f of 1 is equal to 8. And then we're going to write it in 2 forms, but let's just start with the first form. F of x equals. I just said the first thing we should write down is what? Is the leading coefficient, which we don't know right now. A. But write it first. X minus, x minus. How many of these are we going to have? 3. It said degree 3, right? X minus. 3 of them. So clearly the next step is to fill in those blanks. Okay, first number? Not quite 3. -3, the way I've written it. You can change it to an x plus 3. But x minus -3 is what we have, right? X minus the first guy. There. Okay, that was good. So I got an I. So what are we putting in? This x minus I, right? That just goes right there. It's x minus each 0. But we were only given 2 and we're expecting 3. What's the other 0? It's -I. Remember what we said is that if you have something like 3 plus 4i as a 0, then automatically 3 minus 4i. If you have a single I, okay, I'll stress, it's a plus and it's a 0. What's the conjugate of 0 plus I is 0 minus I. So -I is the other piece. And so for sure you should expect a problem where I give you one imaginary number. I'm not going to tell you the other one is there, but you need to know I got to put the conjugate partner in there, right? It's going to feel like some information is missing. That's my way of testing whether you know that these guys come in pairs. Okay, so this is good here. We still need to confirm or make it so that f of 1 is 8. What's the only freedom we still have left in this equation? Yeah, we're going to plug 1 in for the x's and 8 for the output, the y. And what are we going to solve for? A, right? A is the freedom that we have. And if you had forgotten to write down the A, you'd look at this and say, well, shoot, f of 1 equals 8, unless we're really lucky, it's not going to be true. And you're not going to know how do you like resolve that. You don't have control over any of the x minuses, but you have control over this number here. So let us solve. 8 equals a times, let's see, 1 plus 3 there, 1 minus I there, and then 1 plus I there. Right, that's what we're after. And we're going to solve for a. 8 equals a times, all right, so there's a 4. Let's save a little bit of time here. It is possible, I'm going to write something that I don't want you to write. So this part in orange, don't copy. What you could do is distribute the 4 into the first parentheses, yes? And then whatever you get, you could distribute like a foil or lobster claw into the second parentheses. It's totally fine to do that. But if you do, you're missing a shortcut here. When we do if we just distribute here, something nice happens. Yeah, there's going to be canceling here. When you do the outers, what do you get? Plus I, and the inners, minus I, and they cancel. And they're always going to cancel when you have the conjugate stuff happening here. What's that? And I squared is -1. And so it's just better to multiply the two conjugate guys together first. It's not wrong to do the other way, but it's easier this way. Okay, so I think we're good to go here. So the first times first is 1, last times last is minus I squared. Yeah, and then we remember I squared is really -1. So I think we're pretty close on this one. 8 equals a times 4 times 1 plus 1. Okay, so we just got to finish here. 8 equals a times 4 times 2. So how much is a? What? Well, that's kind of disappointing to me as a math teacher, because if you had just forgotten to put the a, then you'd gotten it right anyway, right? All right, so that's not going to happen on the test. Okay, so then I think we're good. We just so we just changed this. We figured out that a is 1. Okay, this question asked us to write the answer in 2 forms. It said factored form and it said standard polynomial form. Which one do you think we have here in blue? That's factored form, right? You can see the factors. So polynomial form is where we distribute everything out. Let's give that a shot. So this is just going to be a big distributing problem. I kind of run out of space up here. I'll go up to the top. Okay, so rewriting this guy, f of x equals, it was a 1 times an x plus 3 times x minus I times x plus I. Do I have that right? Just changing the 2 negatives to a plus. Okay, all we have to do is lots of distributing. But again, if we do it in the right order, it's going to be easier. What you could do is distribute here, right? Lots of foiling here and here. Don't do that. It's not wrong, but it's not the best way. Again, you want to multiply together the conjugate guys first. Good things happen when you do that. So I'm copying the first stuff. F of x equals, oops, x plus 3 times. First times first. X squared. Outers. Plus x times I, inners, minus x times I. Poof. Right, that's why we want to multiply these first. And then the last, minus I squared. There we go. And again, I squared is -1, so this really becomes plus 1 there. And just like that, the i's all magically vanish, which is kind of nice. Okay, so we'll get our final answer now by doing one last FOIL. First times first, x cubed plus, let's do the inners next. 3x squared, outers, plus x, last, plus 3. That's it. Standard polynomial form. Okay, so we've got like half an hour, and I think the activity is a reasonable length today. So if it happens, you are a speed demon and finish early, I know that you still have problems from the last activity that you had not near enough time to do. So we're working on this. Anybody finishes early, go back and start filling in some of those other ones.